Good afternoon, students.
Good afternoon, sir.
Audio is okay.
Yes, sir.
So great. So let us start. So in last class, I was telling you about the standard form for the linear program. So in continuous of that, let us have this question. Two products are manufactured in a machining center. The production time per unit of product 1 and product 2 are 10 and 12 minutes respectively. The total regular machine time is 2500 minutes per day. In any one day, manufacturer can produce between 150 to 200 units of product 1, but not no more than 45 units of product 2. Overtime may be used to meet the demand of an additional cost at an additional cost of $0.50 per minute. Assuming that unit assuming that the unit profit for the product 1 and product 2 are $6 and $7.5 respectively. Formulate the problem as an LP model. So in this case, if you assume let x1 and x2 be number of product 1 and the number of the product 2. So profit is given to you. So maximize z is equal to 6x1 plus 7.5 x2, because unit profit is given to you as a 6 and 7.5. Subject to, now for manufacturing the product 1, the time taken is 10 minutes and 12 minutes respectively. So it will become 10x1 plus 12x2, and maximum availability is 2500 minutes. Then after, you cannot produce, or the production can be between 150 to 200 and no more than 45 for the product 2. So it is given to you x1 less than 200 and x1 greater than 150 and and x2 less than, not more than 40, so less than 40, and production cannot be negative, so x1 comma x2 non negative. Now in the question it is given to you, overtime may be used to meet the demand at an additional cost of $0.50 per minute. So this is the 45. This is 45. So here, what is the thing? Means this much you have. This is the production time. Now this 2500 may be is equal to, may be greater than, and may be less than. So if 10x1 plus 12x2 less than 2500, there is no problem, right? Because we have the extra time. But 10x1 plus 12x2 greater than 250 means you require the additional time. So when it is a less than, you have to add the slack variable. When it is the 10x1 plus 12x2 greater than the 2500, you have to add subtract the surplus variable, so it will become the x3 plus. And whatever the surplus you are taking, for that you have to pay the 0.50, right, at the additional cost of this. So from the profit, this cost you have to subtract. So it means this constraint will become the 10x1 plus 12x2 plus x3 minus x3 plus is equal to 2500. So it is already in is equal to form. Here you have to add the slack variable s1. So it will become the x1 plus s1 is equal to 200. Here you have to subtract the surplus variable. So it will become x1 minus s2 is equal to 150. Here you have to add the slack variable. So it will become x2 plus s3 is equal to 45, and x1, x2, x3 minus x3 plus s1, uh, s1, s2, s3 all are greater than equal to 0. So this is nothing. This is the unrestricted inside. This can be positive, this can be negative, this can be 0. So this is the unrestricted inside, right? So this is the URS. This is your URS. So here x3 minus is what? It is the unused time. It is the unused time. And what is the x3 plus? It is the extra time required. Extra time, additional time required. Clear this part? So that is the clear this thing. So combining these two will be the x3. So x3 can be x3 is equal to x3 minus x3 plus, right? So it will be the URS, unrestricted inside. So that is the way to tackle the unrestricted variable. The same thing here we have done. Clear? Here just for the notation they have written the x3 plus, but conventional is the we should use the minus, and here we should use the plus. Later on I will tell you why I am writing the minus, because here it represents the unused time, right? And here we require the additional time. That's why we add the here the plus. Now next question, very important question. Joe shop manufactures 3 products whose unit profit are 253. So let us have the x1, x2, x3 be the number of product 1, 2, and 3 respectively. The company has wasted 80 hours of labor. The company can afford 80 hours for the labor and 65 hours for the machine. 65 hours for the machine time for the production of the 3 products. The labor requirement per unit of product 1, 2, 3 are 212. So it means it is the 2x1 plus x2 plus 2x3. The corresponding machine time required per unit are 112. So it will become x1 plus x2 plus 2x3. And here in the first line profits are 253. So it means we have to maximize z is equal to 2x1 plus 5x2 plus 3x3. 3x3. This is the optimization and subject to this. Now Joe shop regards the wasted labor and machine hour as a goal that may be exceeded. So so it can means it is not necessary this 80 hours or 65 hours are enough if necessary, but the additional cost, but at the additional cost of $15 per labor hour and $10 per machine hour. So it means this 80 may be enough. This 80 may be enough, or may not be enough. Similarly, so similarly, machine time may be enough, may be enough, but may not be enough. So when it is not, so here we can say if it is enough, we have to add the uh, x4 minus. If it is not enough, then we have to subtract the surplus. If 65 is enough, then we have to add the select variable x5 minus. If it is not enough, then we have to add the subtract the surplus variable x5 minus. So what is this x4 plus and x5 plus? These are the additional time, and for the additional time you have to bear some cost. So that cost you have to subtract. That cost you have to subtract from the profit. So x4 plus and minus 10 x5 plus. And here x1, x2, x3, x4 minus, x4 plus, x5 minus, x5 plus, all are non-negative. So this is the standard way to write the problem in the standard form. Yes, any doubt?
No, sir.
Great. Now, this is the theoretical question. In an LP in which there are several unrestricted variables, the transformation of the type xj is equal to xj minus minus xj plus, xj minus and xj plus greater than equal to 0 will double the corresponding number of non-negative variable. Generally, when I'm saying that, okay, just will so we can instead replace the k unrestricted variable with exactly k plus 1 non-negative variable using the substitution xj is equal to xj dash minus w, where xj dash and w greater than equal to 0. Use the Torah to solve this. So in this case, it is given to you x1 is non-negative and x2 and x3 are unrestricted in sign. X2 and x3 are unrestricted in sign. So when x2 and x3 are unrestricted in sign, so x2 can be written as x2 minus minus x2 plus, and x3 can be written as, when x2 and x3 are unrestricted in sign, it can take any value, negative, 0, positive. So for that, but in the standard form, we require only the non-negatives. So we replace the unrestricted variable with the two non-negative variables x2 minus minus x2 plus. Similarly, x3 can be written as x3 minus minus x3 plus. So our problem will become maximize maximize z is equal to minus 2x1 plus 3 x2 minus minus 3 x2 plus minus 2 x3 minus plus 2 x3 plus, right? This we can write subject to 4x1 minus x2 minus plus x2 plus. Everywhere you replace the x2 by the x2 minus minus x2 plus, minus 5 x3 minus plus 5 x3 plus is equal to 10. And this we can write 2x1 plus 3x2 minus minus 3x2 plus 2x3 minus minus 2x3 plus is equal to 12. So actually what is happening here, we have the two variables, two unrestricted variables to tackle the two unrestricted variable. We are using the four non-negative variables, right? Means number of the variables increase by double. Now they are suggesting, instead of doing that, what you can do, you can do x1, you can do the x1 is equal to x1 dash minus w, and x2 is equal to x2 dash minus w. Means this w is common in all. This w is common in all. So what will happen? Due to this, we can write maximize z is equal to minus 2x1 plus 3x2 dash plus 3x2 dash plus minus 3w minus 2x3 dash plus 2w plus 2w. Ultimately, it will give you minus w, right? So it will become minus 2x1 plus 3x2 dash minus 2x3 dash minus w. Subject to it will become 4x1 minus x2 dash minus 5x3 dash, and it plus 6w is equal to 10, and this will give you 2x1. So 2x1 plus 3x2 dash plus 2x3 dash minus 5w is equal to 12, and here x1 comma x2 dash x3 dash and w greater than equal to 0. So what is the benefit? Here we have the two unrestricted variable, x2 and x3. Here we have the two unrestricted variable. For tackling the two unrestricted variable, we are using only the three non-negative variable. So they are saying that this can also work. So here we have done the same thing. So when we compute the solution, here you can see we have the x2 plus 6.15 and x2 minus as a 0. So x2 will come, they have taken, I think they have taken the x2 is equal to x2 plus minus x2 minus. Just it is the notation, don't confuse between the x2 plus and x2 minus. In practice we take x2 minus minus x2 plus, but here this, in some places they have taken the x2 plus minus x2 minus. So don't confuse with that, it is just notation. So it will come the 6.15 minus 0, that is the 6.15, that is the this 6.15, and here we have the x3 plus x3 minus. So x3 is equal to what? It is the x3 plus minus x3 minus. So its value is the 0 minus 3.25, that is the minus of the 3.23. So here we have the value. Now instead of doing that, if you take the w, so here the x2 is coming this, x3 is coming this, and w is the same thing, w is the 3.23. So when we compute the x2 as a x2 dash minus w, x3 as a x3 dash minus w, you will get the same x2 and x3. So whatever the approach you follow, right, it's up to you, but we prefer this only. Because it does not create the problem, right? Means confusion. By seeing the computationally, it makes the question easy, right? But in practice we prefer this one. Clear? Any doubt how to tackle the unrestricted sign? Very important thing it is. Yes. Now transition from the graphical to the algebraic solution. So I have, in the previous classes, I have solved many questions by the graphical method. So whatever the things we have done in the graphical method to find the solution, the same thing we will repeat, right? And that is the transition from graphical solution to the algebraic solution. Algebraic solution is, from the algebraic solution we can determine the solution of any number of variables, any number of the constants. So what is that? So in the graphical solution, you have first you have what you have done. Graph all the constant, including non-negativity restriction. Generally, we graph, right? We graph like this. All the constant we graph. Solution space consists of the infinitely feasible solution. If this is the solution space, if this is the solution space, so here we have the infinitely feasible solution. Identify the feasible corner point. Then we identify the feasible corner point. Then we identify the feasible corner point. Then candidate for the optimum solution are given by the finite number of the corner point, and we put all the corner point in the objective function, and which one will give the maximum or minimum value, that will be the optimum corner point, right? So that is the methodology we do in the graphical solution. The same thing we will do in the algebraic thing. Means for drawing the constraint, what we have done, we have converted all the constraint into the equation form. So that's here also we will do. We represent all the equation in the equation form. So when we present in the equation form, we have the m equation and n variables. Total we have the m equations and n variables. Restrict all the variables. Restrict all the variables should be the non-negative. So here it is very necessary that all the variables where unrestricted in sign, negative variable, positive variable, whatever the thing, all the variable must be the non-negative only. And here we have the m less than n. Then we determine the feasible solution space. We determine the feasible solution space, and from the feasible solution space, we see which one is the feasible basic solution. Which one is the feasible basic solution, and from the basic feasible solution, we determine the optimum basic feasible solution. So how we do this, that we now proceed. Means the same thing we will do, right? Only whatever there we write, we shaded the region. That shaded region is nothing, that is the basic feasible solution. That is the feasible solution. That is the feasible solution. And corner points. And corner points are the basic feasible solution. And among the basic feasible solution, one is the optimum, right? Optimum basic feasible solution. Means feasible solution is nothing, it is the shaded region. Basic feasible solution is nothing, it is the shaded region. Shaded region in the graph. Basic feasible solution is nothing, it is the corner point. It is corner point. And the optimum solution is the optimum corner point. So how we do this? So preview of the simplex algorithm. So in this, first we have to take the idea what is the basic variable, what is the non-basic variable. So let us discuss it one by one. So let the LP with m constraints into the standard form contains the n variable. So after handling less than equal to constraint by the slack variable, greater than equal to by the surplus variable, and unrestricted variable by two non-negative variables, we convert our LP into the standard form with m equations and n variables, with m equations and the n variable, that we can write in the matrix form as a AX is equal to B, where A is what? A matrix of dimension m cross n. X is what? It is the x1, x2, xn. So it is the column vector, right, of dimension n cross 1 is equal to, we have the right hand side, that is the m cross 1, right? So here we have the m equations, here we have the m right hand side. So m cross 1, and here we have the n variables. So that is the structure of the matrix structure of the our LP problem. So from the matrix theory, you know, if m is equal to n, number of equation, number of variables are equal, then we have the unique solution. If number of equation less than the number of the variable, so few variables you have to assume as a is equal to 0. Means how many variables for the unique solution? You means I am saying that when m is less than n, then for the unique solution, you require the m variables only, right? M equation and M variables, M variables, right? So n minus m variables, we presume that they are equal to the zero. So non-zero m variables and m equations will give you the unique solution, right? Listen carefully. N minus m variables we presume as a zero, and remaining m non-zero variables with m equations will give you the unique solution. Then case 3, when number of equation m greater than the n, then we assume that m minus n equations are redundant equation. Redundant equation means n equations, and n equation and n variables will give the unique solution, right? M minus n equations are redundant, right? They are the redundant. Only the n equations and n variable will give you the n unique solution, right? So this we know from the matrix theory. Now uh, we have the system of equation ax is equal to b. The basic solution of ax is equal to b is obtained by setting n minus m variable equal to 0, and those n minus m variable are known as the non-basic variable. Those variables are known as the non-basic variable, which you equate to 0. And the non-zero x or remaining non-zero x, right? That will give you remaining uh, remaining m variables. No, it is not remaining m variables are known as the basic variable. So non-basic variables are always 0, basic variables are non-zero, right? No, not exactly non-zero, non-negative, right? Maybe some basic variable may also come the 0, but non-basic variable non-basic variable are always 0. Non-basic non-basic variable are always 0, and basic variable are greater than equal to 0. uh, Most of the case positive, and in some cases it may be the 0, but that is not a non-basic variable. But non-basic variable are always 0. For example, if we have the question, minimize z is equal to 3x1 plus x2, subject to x1 greater than equal to 3, subject to x1 greater than equal to 3, and x1 plus x2 less than equal to 4, and 2x1 minus x2 is equal to 3. So here you have to add the here you have to subtract the surplus variable. Minus e1 we have subtracted. Here you have to add the slack variable plus s1 we have subtracted. There in this there is no need of the slack variable, no need of the, because it is already in the is equal to form. No need of the slack or surplus, and all the variables are non-negative. X1, x2, e1, s2 all are non-negative. So here you can count number of equation. Number of equation will be the 1, 2, 3. Number of equation are 3. So here the m is equal to 3. Number of variables will become x1, x2, e1, s2. The number of variable will be the n is equal to 4. So n is equal to 4 means we say that n minus m is equal to 1, means any one out of 4 any one is the non-basic variable, and remaining 3 will be the basic variable. Means if x1 is a non-basic variable, then basic variable will be the x2, e1, s1. If non-basic variable is x2, then the basic variable will be the x1, e1, s1. If the non-basic variable is e1, then basic variable will become the x1, x2, s1. If non-basic variable is s1, then basic variable are x1, x2 and e1. Clear this part? Clear this part? So if you draw, the constraint, right? So first constraint is what? First constraint is x1 greater than equal to 3. X1 greater than equal to 3. So for the graph, we make it is equal to x1 is equal to 3. So this is the line of x1 is equal to 3. This is the line of x1 is equal to 3. Then second equation, x1 plus x2 is equal to less than equal to 4. So we make it is equal to 4. So x1 plus x2 is equal to 4. So x1 plus x2 is equal to 4. So this is the line of x1 plus x2 is equal to 4. In the graphical solution, this is the x1 plus x2 is equal to 4. Then in the third one, we have 2x1 minus x2 is equal to 3. 2x1 minus x2 is equal to 3. So this is the line of 2x1 minus x2 is equal to 3. So here we have the constraint. So the feasible region is x1 less than x1 greater than equal to 3. So x1 greater than equal to 3 this side. Then we have the x1 plus x2 less than equal to 4. X1 plus x2 less than equal to 4 this side, right? And we have the 2x1 minus x2 is equal to 3. 2x1 minus x2 is equal to 3. This line only, right? So below this, so I think for this problem we haven't the feasible solution, because only on the line we are getting. So this side, this, so no feasible region. Main thing is now another thing we have to convey here. So here we have the corner point O. Here we have the corner point G. Here we have the corner point F. Here we have the A, intersection of these constant, B, C, D, and E. Right? So I have already written the and here we have the H. So in this case, presently I am writing only the x1 x2 is equal to x1 x2 values. But over this line, what is this? X1 is equal to 0. X1 is equal to 0. Over this line, what is the x2 is equal to 0? X2 is equal to 0, right? And over this line, E1 is equal to 0, and over this line, S2, over this line, S2 is equal to 0. Over this line, S2 is equal to 0, right? S2 is equal to 0. And over this line, what we have? Is equal to means, here we have the S2 is equal to 0, and here we have the 2x1 minus x2 is equal to 3. So these are the equations. So what now please see here the table. If the x1 is the non-basic variable, non-basic variable means x1 is equal to 0, x1 is equal to 0, x1 is equal to 0. So from the first equation, what you will get? E1 is equal to minus 3. From the last equation, you will get x2 is equal to minus 3. When you put the x2 in the second equation, minus 3. On this side, if you take you will get the s2 is equal to 7. So x2 E1 s2, right, will be the minus 3 and 7. So here you will get the solution minus 3, 7. When you take x2 is equal to 0, so x2 is equal to 0 means we have the x1 minus E1 is equal to 3. X2 is equal to 0 means x1 plus s2 is equal to 4 and x2 is equal to 0 means 2x1 is equal to 3. 2x1 is equal to 3. So x1 will come 3 by 2. So when we put the x1 is equal to 3 by 2, you will get the e1. When we put the x1 is equal to 3 by 2, you will get the s2. So here the x x1 e1 s2 will come 3 by 2 minus 3 by 2 and 5 by 2. Similarly, e1, if you take e1 is equal to 0, so x1 x2 s2 will come 3 3 minus 2. If you take s2 is equal to 0, then x1 x2 e1 will come 7 by 3 5 by 3 minus 7 by 3. So here x1 x2 is what? 7 by 3 5 by 3, the point f. x1 x2 is equal to what? 3 comma 3, point e. x1 is equal to 3 by 2, x2 is equal to 0. Right? This implies x1 is equal to 3 by 2, x2 is equal to 0. So point A. Here x1 is equal to 0 and x2 is equal to minus 3. That is the point H. So in this case, we have the x1 is equal to 3, x2 is equal to minus 3, H. And then after H is the first point, then A is the x1 is equal to 3 by 2. A. So this is the A is equal to 3 by 2 comma 0. Then after we have E and F. So 3 comma 3, E and F. So here we have the 3 comma 3 and F. F where we F is this one, 7 by 3 5 by 3, this point F. So here now they are saying that which one is the feasible, they are the feasible or not. So they, no point is the feasible means which satisfy all the constraints. So out of the A, H, E, F, no one is the basic feasible point. So no basic feasible point because it does not satisfy all the constraints. So BFS is this. Clear? Now, if we have the problem maximize z is equal to 2x1 plus 3x2 subject to x1 plus x2 less than equal to 6, 3x1 plus 2x2 less than equal to 6, x1 comma x2 greater than equal to 0. Express the problem in the equation form. In the equation form means here you have to add the select variable s1, here you have to add the select variable s2, and here the s1 comma s2 greater than equal to 0. So that is the equation form. Determine all the basic solution of the problem and classify them as a feasible and infeasible. So in this case, we have the m is equal to 2, number of equation is equal to 2, and n is equal to 4, number of variables are x1 x2 s1 s2. So number of variable will be the 4. So n minus m will be the 2. N minus m will be the 2. So number of the non-basic variable, number of the basic variable. So here if you take the x1 x2 as a non-basic variable, automatically s1 s2 will be the basic variable. If you take the x1 s1 as a non-basic variable, then x2 s2 will be the basic variable. If you take x2 s1 as a non-basic variable, so x1 s2 will be the non-basic variable, x1 s2 will be the basic variable, and if you take the x2 and s2, x2 s2, so it will become x1 and s1 as a basic variable. And what other combination will come? If you take the s1 s2 as a non-basic variable, so x1 comma x2 will be the basic variable. Anyone is remaining? Actually 4c2 point होगा ना, x1 x2 x1 s1 and x1 s2 x1 s2 I have not taken na. So x1 s2. So x1 s2 if you take, so it will become here the x2 and s1, x2 and s1. So these are the total combination. So using this you can determine the unique solution. So here we have the unique solution. So in this case, if you take the basic variable x1 x2, basic variable x1 x2, it means s1 s2 are non-basic variable. So our system of equation will be the x1 plus 3x2, x1 plus 3x2 is equal to 6, 3x1 plus 2x2 is equal to 6, and it will give the solution 6 by 7, 12 by 7. And for this x1 x2, the z is equal to 6 and 6 by 7. And on the graph it is the point B. On the graph it is the point B. So on the graph it is the point B. Clear this part? Similarly, second combination, if you take the basic variable x1 x3, x1 x3, it means x2 x4, x4 either you say x4 or s2 or s2, right? Means they have added the slack variable x3 and x4, but whatever we are representing as a s1 s2, it's up to you, any name you can give. So so here, when we have the basic variable x1, x1 x3, automatically it implies that x2 and x4 are the non-basic variable. Non-basic variable means they are equal to 0. So from the system of equation, the value of the x1 x3 will come 2 comma 4 and z is equal to 4, and that is the point E. So that is the here the point E. Here we have the point E. This is the point E, right? X2 is equal to 0, so and x1 is equal to 4. Then after, similarly, you take the all the combination. So here we have the point B, point E, point C, right? Then point A, point D, and then point F. So here one thing you can note. What you have to note? I am saying that in the standard form, x1, x2, x1, x2, x3, x4 must be non-negative. Must be non-negative. Here, here the x1 x2 is coming positive positive, and x3 x4 is equal to 0, correct? Here the x1 x3 is the 2 4, right? And x2 x4 is equal to 0, correct? It is the feasible. But here the x4 is non-negative, negative, so it is not feasible, not feasible. In this case, here the x3 is negative, not feasible. In this, x2 x4 positive, and x1 x3 is equal to 0, so right, so correct one. And here 6 and 6 positive, and it is what, x3 x4, so x1 x2 is equal to 0, x1 x2 is equal to 0, so it is the point F. So here you can see, in the graph, this point is not feasible, and this point is not feasible. This point is not feasible. Only out of the 6 points, out of the 6 point, 1, 2, 3, 4, 5, 6, 4 are feasible. 1, 2, 4, 5 are feasible, and third one and sixth one are not feasible, right? So here it is written, so whatever we are doing in the graph, the same thing we are doing the algebraically. Am I clear? And out of these feasible point is the this one is the feasible point, this one is the feasible point, this one is the feasible point, this one is the feasible corner point. So these are the basic feasible solution, these are the basic feasible solution, these are the basic feasible solution, these are the basic feasible solution. And out of these basic feasible solution, which one will give you the maximum value of the z, which one will give you maximum value of the z, that will be the optimum. Right here the z is equal to 0, here the z is equal to 6, here the z is equal to 4, but here the z is 6 and 6 by 7. So there we compute the this will give you the optimum value. So this point 6 by 7, 12 by 7, 6 by 7, 12 by 7 is the optimum solution, this is the optimum solution. And for the non basic feasible solution, for the non basic feasible solution, we never compute the value of the z, right? We never compute the value of the z, because that point are not those points are not feasible points, so no need to compute the value of the z. Clear?
Sir, what method do we use to check the feasibility of a solution? Do we use
Actually we are making the base of the simplex method, you have to use the simplex method. All these concepts I will transform to the simplex method. Simplex method will come, I think, in next to next class, and that is the most important thing of your course.
okay, sir?
In this, any doubt in the graphical transition from graphical to the algebraic? Actually, whatever we have conveyed in the graphical solution, the same thing I tried to convey in the algebraic solution. Any doubt in transition? Means try to understand, this line is what, this line represent the x1 x2 is equal to 0, this line represent the x1 is equal to 0, this line this line represent the x3 is equal to 0, and this line represent the x4 is equal to 0, right? So actually here we have the lines, we have to draw the four lines. Clear? So that's all from my side for today.
Thank you, sir.
Welcome, have a nice day.